Okay, so this is our last video for our unit on electromagnetic radiation. To wrap things up, I want to go over the Doppler effect. You've probably noticed the Doppler effect at some point. If a police car is parked and its siren has a frequency of 1,000 hertz, or 1,000 oscillations per second, then that frequency that you will hear. On the other hand, if the car is driving towards you at 75 miles per hour, then the frequency you will hear is about 1,100 hertz. So the sound will have a noticeably higher pitch. If the police car is driving away from you, then the frequency will have a lower pitch of about 900 hertz. So as the police car drives by, you will hear a noticeable drop in the pitch or the frequency. The reason for this is that whenever the source of a sound is moving relative to the listener, there is a shift in the frequency that the listener hears. The reason for this is that each time the police car produces a new sound wave, the car is a little bit closer to the person on the right and a little bit further away from the person on the left. That means that each sound wave moving to the right arrives at the listener's position a little bit sooner than it would have if the car was stationary. On the other hand, the car is a little bit further away from the listener on the left, so each sound wave arrives a little bit later than it would if the car was stationary. That means, from the listener's point of view, when the source of a sound is moving towards you, the frequency is a bit higher than the frequency of the source. And if the source is moving away from you, then the frequency of the sound is lower than the frequency produced by the source. The shift in the frequency caused by the source and listener moving relative to each other is called the Doppler effect. Notice that the frequency produced by the siren is exactly the same the whole time. The only thing that is changing is the relative velocity between the car and the people listening to the siren. To be a bit more quantitative about this, I'm showing you the low-speed formula for the Doppler shift. The shifted frequency is equal to the original frequency that is produced by the source times 1 plus or minus the relative speed of the source and the listener, divided by the speed of the wave. If the source and the listener are moving towards each other, then you use a plus, because the observed frequency is higher than the frequency of the source. And if they are moving away from each other, then you use minus. The speed of sound is about 340 meters per second, so earlier I picked a cup speed of 34 meters per second, so that gives you a shift in frequency of about 10%. I've described the Doppler effect in sound because that's most likely where you've noticed it before. However, it is universal to all waves, and it occurs in electromagnetic waves, including microwaves and visible light. For example, police use the Doppler effect to determine the speed of a car. A radar unit beams microwaves with a frequency f at an oncoming car, and then measures the frequency of the microwaves that are reflected off of the car. The microwaves that are reflected off of the car have a higher frequency than the original wave, and the device can determine the speed of the car. With the higher frequency of the reflected wave, the higher the speed. Some enterprising individuals counter this by running a noisy microwave generator with lots of different frequencies to confuse the radar unit, although modern units are pretty good at ignoring this noise, and it's also very illegal. The Doppler effect on light has allowed astronomers to determine the speed of stars and galaxies relative to the Earth. To see this, we have an animation showing the color that you would see if a yellow spaceship traveled to the right. If the spaceship is traveling towards you, you see a blue shift with frequency of the light increasing, which means that the wavelength of the light has decreased, so the light appears to be bluer or blue shifted. If the spaceship is moving away from you, then the light you see will appear to be redder or red shifted and have a lower frequency and a longer wavelength. To be more quantitative, we have our formula for the Doppler shift of light, which is exactly the same as our previous formula, although now we use the speed of light, so 3 times 10 to the 8 meters per second, for the velocity of the wave. Notice to get a meaningful Doppler shift, you need a relative velocity to be some meaningful fraction of 3 times 10 to the 8. So you have to be moving awfully fast to observe the Doppler effect with light. Okay, so let's try an example. A galaxy is receding from the Earth at 0.05 c. So 0.05 c means it is 5% of the speed of light, and so what wavelength will be observed for light emitted by a galaxy with a wavelength of 500 nanometers. To do this, we write down our equation for the Doppler effect. We notice that the galaxy is receding, so it is moving away from Earth, so we expect the frequency to be lower and the wavelength to be longer. That means we use the minus version of the equation. Next, we need to find the frequency of the light. So we rearrange our frequency wavelength formula. So we have the speed of light is 3 times 10 to the 8, and we divide that by the wavelength to get the frequency. So we do the math and get our light has a frequency of 6 times 10 to the 14 hertz. Now we plug this into the Doppler formula. So the original frequency is 6 times 10 to the 14, and the velocity of the galaxy is 0.05 c, meaning versus the speed of light, which is c. So that means we are because we are moving away from each other, we use minus, and that gives us a new frequency of 5.7 times 10 to the 14 hertz. To finish off the problem, we recalculate the wavelength using c divided by frequency being equal to the wavelength lambda, and when we do that, we find that the new wavelength is 526 nanometers. So yes, the light is slightly redder than it started. So 500 nanometers is sort of a cyan color, while 526 is pretty much a green, so it is a redshift. Also, remember the 0.05 c speed, that is 3 times 10 to the 8 times 0.05, so I don't think it's just 0.05. So the most famous application of the Doppler effect in light comes from astrophysics. Edwin Hubble and Henrietta Leavitt determined that you could find the distance from the Earth from other galaxies by measuring the intensity of light from a special kind of star called a Cepheid variable. They found out that they could find the relative velocity of other galaxies using the Doppler effect. Because the atomic lines caused by hydrogen atoms and other elements in distant stars are well known, they could find the position of the line that we see, and then by using the difference to figure out the Doppler shift, and then if you know the Doppler shift, you can find the relative speed of the distant galaxy with respect to Earth. One of the early graphs of this is shown on the left here, and the results are surprising. First of all, other galaxies are moving away from our galaxy, so all of them. And more surprising, the further away the galaxy, the faster it is moving away from us. The best way of understanding this is to think that the entire universe is expanding like the space-time itself. So the idea that the entire universe is expanding is a fascinating result, and if we think about it, we can retrace the expansion, and 14.7 billion years ago, the entire universe would have emerged out of a single spot in some kind of a Big Bang. That is telling us that the universe seems to have formed 14.7 billion years ago. Special relativity tells us that time and space are intertwined, so you cannot really have time without space or space without time, so it also kind of implies that time itself began 14.7 billion years ago as well. This probably goes beyond the mandate of this course, but it is kind of amazing that science can answer some of the sort of hardest origin questions that we often wonder about. Does the universe have a beginning, and what was there before the universe? Well, the universe does appear to have a beginning, and both time and space seem to emerge from that beginning, so the concept of time before the Big Bang doesn't really make any sense. I'm not sure how satisfying these answers may be, but the fact that we have a kind of clear answer to it is kind of amazing. Alright, so that's it for our unit on electromagnetic radiation. So don't forget you have one more question here to work out with the Doppler shift, and then also you guys have a homework due